Hi everyone, welcome back to ChemVault. In this master's level session, we are covering one of the most important and most feared topics for GATE and CSIR net chemistry, pericyclic reactions. By the end of this video, you will be able to confidently predict whether a reaction is thermally or photochemically allowed, whether it goes con- conrotatory or disrotatory, superficial or intrafacial, using nothing but electron counting and a couple of simple rules. We'll build this up in the four parts: electrolytic reactions, cycloaddition, sigmatropic rearrangement, and any reactions. Let's get started. So, what are pericyclic reactions? So, what exactly is a pericyclic reaction? In simple words, it's a reaction that happens in a single step through a cyclic transition state where all the bonds are made and broken at the same time around a closed loop of overlapping orbitals. There are no carbocations, no radicals, no carbon ions, no intermediate at all. Because of this concentrated nature, pericyclic reactions are highly stereospecific, and this is the key idea for entire topic. The feasibility is decided purely by orbital summary symmetry, by orbital symmetry, not by usual electronic or steric argument you use in ionic or radical mechanism. And here's something that makes the topic exam friendly. Once you understand it, the same starting material can give completely different stereochemistry depending on whether you heat it or shine light on it. That thermal versus photochemical duality is going to come back again and again in this lecture. Then we'll talk about the four classes of pericyclic reactions, which are pericyclic reactions are classified into four major families, and I want you to remember these by their core actions, not just their names. Electrocyclic reactions open or close a ring at the end of a conjugated pi system using just one sigma bond. Think butadiene converting to cyclobutene. Then the cycloadditions brings two pi system together to build a brand new ring with new sigma bonds. The Diels-Alder reactions is the classical example. Then next is sigmatropic rearrangement are about a sigma bond migrating across a pi system to a new position. The Copen-Claisen rearrangement for here. And finally, any group. An in and group transfer reaction involves an allylic CH bond and a pi bond reacting with an enophile all in one concern, concerted step. Keep these four boxes in your head. Every question in this topic falls into one of them. Then next we'll talk about Woodward Hoffman rules and FMO theory. Now let's talk about the theory that explains why these reactions behave the way they do. The first big idea is Woodward and Hoffman's conservation of orbital symmetry, proposed in 1965, which says that as reactants become product, the symmetry of the interacting molecular orbital must be preserved all the way through the transition state. The second is Kinchi Fuki's frontier molecular molecular orbital theory or FMO theory, which tells us that reactivity is governed by the interactions between HOMO of one component and the LUMO of the other. And for bonding to happen, the phases of these orbitals have to match up. Langwitt, Higgins, and Abrahamson gave us correlations diagram which connect reactant orbitals to product orbitals of same symmetry, and when a pathway symmetry forbidden, it forces the ground state reactant to correlate with an excited state product, which means a very high energy barrier. Finally, Devar and Finally, Dever and Zimmerman gave us a shortcut treating the entire cyclic transition state as if it were an aromatic system. That's what we are going to use for most of our rule driving, and it's covered on the next slide. So now is FMO analysis, homo-lumo interaction. Let's see FMO theory in action. In a thermal reaction, the ground state homo of the electron rich components, say the diene, overlaps with the ground state LUMO of the electron poor component, the dienophile. But under the photochemical conditions, absorbing a photon promotes an electron from the HOMO to the LUMO. So now the excited state HOMO, which used to be LUMO, is the orbital in control. This single change is what flips the symmetry outcome between thermal and photochemical pathways. Look at the diagram on the right side. This is HOMO of butadiene, side 2. Notice the phases on carbon 1 and carbon 4. This terminal lobe. There's on the same phase, which means superficial bonding is symmetry allowed here, and here's a shortcut towards remembering. Just count the nodes in the relevant FMO. Even number of nodes means the terminal lobes are in phase. Odd number of nodes means they are out of phase. This one trick will save you a lot of time in the exam. Aromatic transition state, Huckel versus Mobius. This slide gives you the fastest way to drive every selection rule in the chapter using the Dever Zimmerman aromatic transition state approach. Draw the cyclic transition state as a ring of overlapping orbitals and count how many times the phase flips as you go around the loop. These flips are called phase inversions. If you have zero or even number of phase inversions, you have Huckel system, basically a simple untwisted ring of the orbital. The Huckel system, a Huckel system is aromatic and therefore loud when it has 4n plus 2 electrons, and anti-aromatic or forbidden with 4n electrons, exactly like benzene versus cyclobutadiene. But if you have an odd number of phase inversions, you have Mobius system. The array has a twist in it, meaning at least one component reacts in an intrafacial sense. A Mobius system flips the logic. It's aromatic and allowed the 4n electrons, and anti-aromatic forbidden with 4n plus 2 electrons. Learn this one Learn this one slide well, and you can drive every single selection rule in pericyclic chemistry from first principle instead of memorizing tables. Now we'll talk about electrocyclic reactions. Controrotatory versus disrotatory. Let's apply all this to our first reaction class, electrocyclic reactions. When a conjugated polyene closes into a ring, the two terminal p orbitals have to rotate so that they can overlap and form the new sigma bond. There are exactly two ways this can happen. In the conrotatory mode, both terminal orbital rotate in the same directions, both clockwise or both counterclockwise. In the disrotatory mode, they rotate in opposite directions, one clockwise, one counterclockwise. Now, which mode is followed depends purely on electron count. For a thermal reaction with 4 and pi electrons, like the 4 electron ring opening of a cyclobutene, the reaction is conrotatory. For a thermal reaction with 4n plus 2 pi electrons, like the 6 electrons ring closure of hexatriene, the reaction is the reaction is disrotatory. Take a moment to actually visualize this rotation because Gate and Net love to test this with stereochemistry production question, where you're given a specific stereoisomer of the starting diene and asked to draw the exact product. Electrocyclic reactions, selection rule, and worked examples. Here's the complete selection rule table for electrocyclic reactions, and I want you to notice the beautiful alternating patterns: 4 pi electrons, thermal, conrotatory, 6 pi electrons, that's 4n plus 2, thermal, disrotatory, 8 pi electrons, back to 4n, thermal, rotatory again, and for every single one of these, the photochemical pathway is simply the opposite of the thermal one. So, cyclobutene opening to butadiene is thermally conrotatory. Hexatriene closing to cyclohexadiene is thermally disrotatory, and octatetraene to cyclooctatetraene is conrotatory again. If you remember nothing else from the slide, remember this one memory rule. Thermal 4n gives conrotatory, thermal 4n plus 2 gives disrotatory, and photochemical always flips whatever the thermal answer is. That one line answers almost every electrocyclic question you'll see in GATE or CSIR net. So now we'll study the topic cycloaddition reactions. The Diels-Alders 4n plus 2 cycloaddition. Now let's move to second class cycloaddition, starting with the most famous pericyclic reactions of them all. The Diels-Alders reaction. This is a 4n plus 2 cycloaddition, a diene contributing 4 pi electrons and acting as a HOMO donor combines with a dienophile contributing to 2 pi electrons and acting as the LUMO acceptor. Together they form a new six-membered ring with two new sigma bonds, and this is important. It happens in a single superficial steps, meaning both components react from the same phase with the 6 pi electrons. Overall, this is a all superficial Huckel aromatic transition state, so it's thermally allowed. The reaction is completely stereospecific. Cis and trans relationships in both the diene and dinophiles are carried through unchanged into the product. Two more things examiners love to test: the endo rule, where secondary orbitals overlap with the electron withdrawing group. Substituted dinophiles favors the endo transition state as the kinetic product, and regiochemistry governed by the so-called orthopara rule, where the largest HOMO and LUMO coefficient pair up preferentially. Then comes the topic of journal selection rule for plus n cycloadditions. Diels-Alder is just one example of a much more general pattern, and this slide gives you the master rule for any m plus n cycloaddition. A cycloaddition is thermally allowed when the total electron count, considering a superficial and intrafacial component, together satisfy Huckel aromaticity. In the transition state, in practice, for simple all superficial case, this just means 4n plus 2 electrons thermally allowed, 4n electrons thermally forbidden, unless one component reacts intrafacially. Look at the table 4n plus 4 plus 2, 6 electrons thermally allowed, photochemically forbidden. That's your dial elders. 2 plus 2, 4 electrons thermally forbidden in the simple superficial sense. It needs an intrafacial component, but it becomes allowed photochemically, which is exactly why alkene photodimerization work under UV light, but not on heating. 6 plus 4 cycloaddition with 10 electrons follow the same pattern as diel-elders, and even 2 plus 2 plus 2 processes like alkyne cyclotrimerization are thermally allowed once you count all 6 electrons together. Next, sigmatropic nomenclature and superficial and interfacial modes. Let's move to our third class, sigmatropic rearrangement. As a sigma bond simply migrates to a new position along a pi system, and we describe this migration using 1 IJ nomenclature. To assign the number, renew the atoms starting from the original sigma bond and count along each fragment to new bond forming atoms in a 1-3 shift. The sigma bond moves from a carbon 1 to carbon 3 across a single allylic pi system. And interestingly, for a simple hydrogen shift, the thermally allowed pathway is antifacial because the superficial mode is symmetry forbidden. Here's although geometrical although geometrical intrafacial hydrogen shifts are very strange strained, so 1-3 hydrogen shifts are actually rare thermally. In a 1 to 5 shift, the sigma bond very often a CH bond migrates from carbon 1 to carbon 5 across a dyne unit, and this one is thermally suprafacial, making it by far the most common and facile sigmatropic shifts you'll encounter, especially in terpenoid chemistry. And once again, there's a general rule trying it all together for I plus j equal to 4n plus 2 electrons. Thermal reactions go superficial, and for 4n electrons, they go superficial and interfacial. Exactly the same Huckel Mobius logic as before, and exactly reversed under photochemical conditions. The 3-3 family, Cope and Claisen rearrangement. The 3-3 family, Cope and Claisen rearrangement. The most important sigmatropic shift for your exam is 3-3 family. So let's look at the two flagship reactions. First, the Cope rearrangement. 1,5-hexadiene rearranging into another molecule of 1,5-hexadiene degenerate, all carbon 3-3 shift going through a 6-member transition states that strongly prefer a chair like geometry over a boat. For the same reasons, chair cyclohexane is preferred. It minimizes 1,3-diaxyl strain with 6 electrons in all superficial arrangements. It's a Huckel aromatic thermally allowed processor. A quick but high yield point, the oxycop variant, where you have a hydroxyl group at the 3 position of the diene, shows a dramatic rate acceleration compared to the plain cope. Second, the Claisen rearrangement, an allyl vinyl ether rearrangement into a gamma delta unsaturated carbonyl compound. This is an oxa 3,3 shift. You are trading a carbon carbon double bond for a much stronger carbon oxygen double bond, which is a major thermodynamic driving force. It also goes through a superficial chair-like transition state. The aromatic version, aryl ether, rearranging to ortho-allyl phenol, followed by tautomerization, is a classic named reaction and a favorite synthesis step for building carbon-carbon bonds in natural product chemistry. The Elder-Ean reaction. Our fourth and final class is the Ean reaction, sometimes called Elder-Ean reaction, has an alkene that has an allylic hydrogen. This is called the Ean component, reacts with a multiply bonded partner called the enophile, all in a single step. Three things happen simultaneously: a new sigma bond forms between the ene and the enophile. The pi bond in the ene component shift over by one position. This is called allylic transposition, and the allylic CH migrates across the to the enophile. The transition state involves three components and six electrons overall. And just like the Diels-Alder reaction, it's all superficial Huckel aromatic transition state, which makes it thermally allowed. There are also a broader family called group transfer reaction. Think of diamide reduction of alkenes or ester pyrolysis through an LEI elimination mechanism where two sigma bonds are exchanged across a cyclic transition state without forming a completely new ring, the way a true cycloaddition does. And just like every other pericyclic reaction we have discussed, the Ean reaction is fully stereospecific with suprafiscal delivery on both components, so the geometry of the starting alkene is retained in the product. Master selection rule summary table. Let's bring everything together in one master table because this is the slide you should screenshot and revise the night before your exam. For electrocyclic reaction, 4 and electron thermal gives conrotatory, 4n plus 2 gives disrotatory, and photochemical always flips it. For cycloaddition, in the simple superficial sense, 4n is forbidden. Think 2 plus 2 and 4n plus 2 is allowed. Think 4 plus 2 again reversed photochemically. For sigmatropic shift, 4n electrons thermally needs a superficial interfacial while 4n plus 2 electron thermally go superficial. Same reversal under light. And for the any reaction, there is no meaningful 4n case, but the 4n plus 2 6 electrons, all the superficial pathway is thermally allowed, and photochemically, any reactions are rare and not typically tested. One exam tip that trips up a lot students. When you're counting 4n or 4n plus 2 electrons, always count the total electrons in the cyclic array of the transition state itself. And don't forget to include lone pair or charges if they are part of the conjugated system, such as in cationic or anionic pericyclic variants. GATE and CSIR net high yield focus areas. Before we wrap up, let's talk about exam strategy specifically for GATE and CSIR net. Point 1, always count electron first. Draw the cyclic transition state. Count your pi electrons and sigma electrons if they are involved before you even think about applying a rule. Almost every mistake students make in this topic is a counting error, not a rule error. Point 2. Practice actually drawing the con-rotatory and disrotatory ring closure diagrams by hand for both thermal and photochemical cases because these show up directly as stereochemistry prediction questions. Point 3. CSIR net is a particular loves precise terminology known the difference between the describing a single component as superficial or interfacial versus describing the overall transition state as Huckel or Mobius. Point 4. The Diels-Alder stereochemistry and endo rules are the perennial favorite practice predicting the major endo product from a given dyne and denophile. Point 5. Know your chair versus board preference for the Cope and Claisen shift 3 shifts and be able to draw the aromatic 6 electrons transition state confidently. And point 6, the big one. Every selection rule flips under photochemical conditions, so if you memorize the thermal rule set really well, you can always drive the photochemical answer by simply reversing it. Key takeaways. Let's recap the whole topic in 4 lines. 1. There are 4 families of pericyclic reactions: electrocyclic, cycloaddition, sigmatropic, and in or group transfer. Every single one of them is concerted and stereospecific. 2. FMO theory working with HOMO-LUMO interaction and the Woodward-Hoffman conservation of orbital symmetry are really 2 different lenses looking at the exact same underlying physics. 3. The Huckel-Mobius aromatic transition state method, even phase inversion means Huckel aromatic with 4n plus 2 odd phase inversion means Mobius. Aromatic means 4n. Let's you drive every selection rule in this chapter from scratch without memorizing separate tables for each reaction type. And 4. Thermal and photochemical pathways of the same reactions are always symmetry, complementary, master 1, and you can always drive the other. That's pericyclic reaction. Fully mapped out for GATE and CSIR net. If this helped you, follow ChemVault and for more master level chemistry content. I'll see you in the next lecture. Thank you.